Okay, so today we're going to do chapter 6. We're going to do this a little bit differently. I have a camera on me. Hopefully, that makes it seem more regular life, not pandemic life. So you can feel like I'm actually talking to you and teaching you and not just some invisible voice on the screen. I also talk with my hands a lot, and a lot of this stuff is conceptual, and we're doing all these motions and whatever. So hopefully that helps you. Um, as far as the test went pretty well. Maybe I made it too easy. The last quiz didn't go so great. So I tried to make them very easy, basic concept type things. No real tricky problems or anything like that. Um, Again, if you have any questions about that, you can email me. The grades should be posted. I had to manually go through and add all of them, but you should be able to see them anyway on your grades on the Wiley Plus. Again, if there's any questions about, just let me know. Okay, so today we're doing a couple new things. So a lot of this has directly to do with the lab you're going to do, the coefficient of friction lab, which I believe is this week. Should be this week, I think, for you guys. Um, so a lot of the concepts I'm going to go over here tie in directly with the lab. You guys have the unique benefit of having me as a professor because I'm one of the probably the only professor that has taught labs at UNLV. So I know exactly what the labs are, and I can coincide them with the lecture. So hopefully that's helpful. Okay, so we have a list of things here like the frictional forces. It's obviously frictional forces go with everything. We have nothing that exists that's 0% friction. We have things that we're constantly working on, like superconductors, where friction essentially goes to zero, but we don't have any of those working in real world everyday use. So friction is a part of your life. You should know it very well, right? So they have a bunch of examples here, picking things up, walking, biking, whatever. Obviously, if there wasn't any friction, then when you're pedaling your bicycle, the wheels are going to spin and it's not going to move anywhere, right? So you need friction for this kind of thing. Uh, yeah. So for those of you taking 182, you'll get into the efficiency of engines and stuff in that class. But just as just an example of how friction comes in play with everyday objects that you may not think about, like your car. So, like, it's using as an example here, 20% of the gasoline used in all automobiles goes to counteract friction in the drivetrain, right? There's a lot of friction in there. That's what your oil is doing. If you should happen to take all the oil out, your car will run for a little while, but basically all those metal components that are rubbing against each other are going to create friction. And through friction, we create heat, right? You're forcing something to grind against something else. So it wants to go faster than it actually can. The frictional force is slowing it down. And when it's slowing it down, we have to lose that energy in some form. So in this case, it's losing it in the form of heat. And the hotter it gets, the metal starts to expand. And then eventually it's expanded so much it can't move. So if you run your car without oil for too long, basically the things are going to rub against each other, things are going to heat up, and then it's going to lock up. You're going to lock up your engine. You're going to basically have to get rid of the engine and get a brand new engine, which these days means you get a brand new car. So that's the point of oil. The point of oil is to lower the coefficient of friction in the engine. And by lowering that coefficient of friction, we're not putting out as much heat so that it can keep going. Okay. A whole wall of text on this slide. They're using an example if you slide a book across the counter. So this means like you take the book, you slide it, and then it just moves along with the initial energy that it was put into it, and it continues sliding until friction slows it to a stop. So that we're basically saying that the forces are parallel to the surface. So anytime you have friction, friction's always working in the opposite direction of the motion. I've had some people mention to me that they get confused where the frictional force is acting. Just remember, it's always opposite of the motion of whatever the object is that is traveling. It's always working against you. Just think about it like that. Friction is never going to work for you. it's always going to work against you. So then the second part of this says, by doing that, when you go to push a book just now at constant speed, meaning I don't give it an initial shove, I'm just pushing it across the desk constantly like this, there is constantly a force going against me. That's the frictional force, right? Because if there wasn't, I could let go of the book and the book would just continue to slide. But I can't do that. I have to keep pushing the book in order for it to keep moving. Then the third example, they're talking about a crate. It's just an immovable object, is basically what they're saying. Something bigger and heavier that if you put all your weight and strength into it, that you can't move it. You're not overcoming that frictional force anymore. That frictional force is now greater than what you can supply. So 3 examples. I'm going to get more into that. So again, with the lab, same deal. You're going to be doing the static frictional force and then the kinetic frictional force. The static is when things aren't moving. The kinetic is when things are moving. That's it. So if you've ever tried to push something heavy, maybe a large piece of furniture, a refrigerator, a couch, anything, you could probably go try it with your couch right now. If it's on carpet, it's going to be a lot harder. If you go to push it, to get it moving is a lot more difficult than to keep it moving. So even if it's on the carpet, when you go to push it initially, you have to put a large amount of force to get it going, and then it starts sliding, and it's much easier. That's basically what these two things are saying. I'll just move on to the next one. So this is also coincides exactly with the lab. So when you guys go to do the lab, you guys are going to see this. You're going to be able to answer the questions at the end of the lab. Again, you should have a unique advantage to that. So there's these different scenarios basically going on. So you have a block sitting on a plane. The block in the first picture is there's no forces being applied in the x direction. The block's just sitting there, right? So the forces must balance each other. The normal force and the force of gravity must balance each other because it's not moving up or down, right? So now we are going to start to apply a force, meaning you're going to put your hand on the block and you're going to start to push it, right? The thing is, you're pushing, but you're not pushing hard enough to overcome the force of friction. So the block doesn't move. And you can see by the magnitude of the arrows we've drawn here and here, they are equal. So this means you haven't overcome that frictional force. It's pushing against you just as hard as you're pushing against it. So we go down here to the third example, and now you're pushing harder. But again, the frictional force matches you in magnitude. So it's still not moving. And again, it's just more of the same, pushing even harder at the bottom of the page down here, and it's still not moving. So once you overcome that, now we are pushing harder than the frictional force. So now the magnitude of the friction has decreased because now the magnitude has changed from the static coefficient of friction to the kinetic coefficient of friction. So now it's sliding. You have that initial momentum going with it, so it's overcome the frictional force that's working against it easier. So you can see that the force we're applying is much greater, which means it's moving. So again, when you go to think about this from a physics textbook problem standpoint, you're going to want to look at the same, you're adding and subtracting forces that are in the same direction, right? Same thing. You're breaking it down to components, X and Y, and then we're going to add those forces. And then without even having a picture, we can actually tell what's going on if you just add them correctly. So if we go down here, we're saying maintaining speed, then you can use less force to maintain the speed because the coefficient of friction is weaker than the static of friction. And then this is a plot down here at the bottom. And I just drew over the axis of time. But they're basically saying this is the magnitude of the frictional force. This is the time. So as you apply a force along here, I'm applying a force. The force is growing. I'm pushing harder and harder and harder and harder until I get to this point. When I get to the peak of this, basically now I am matching the frictional force that's pushing against me. So up here is the static, where the static force is, the static frictional force at its peak up here. If I push exactly as hard as that's pushing back at me, the block's not going to move. Again, this relates directly to your lab. So the moment I overcome this in the slightest way, then the block's going to start to move. When the block starts to move, all of a sudden the amount of friction or the amount of force required drops off substantially here. So it drops off, and then you apply this constant force through here, and that is the kinetic portion. Now, this plot, it's going to be pretty much the same for any object, no matter what it's made out of, but the magnitude over here, the total amount that it's reaching, is going to be different. Obviously, if you go to push something on ice, then it's going to be really low. It's going to be like something like here, right? And then continue on. But if it's something like you're pushing a piece of a wooden block on a piece of rubber, it's going to be much higher, right? Coefficient of friction is going to be much higher. There's actually no way to figure out what the coefficients of friction are. And I think they're going to write this. Okay, I'll save it for the next slide. We'll just move on here. So again, we're showing kind of a closer up image of two objects rubbing against each other. So if you look at them, they're not necessarily smooth once you get down to a certain magnification of them, right? There's little bumps in there. Even if you get down to the molecular size, you're still going to have a friction of atoms rubbing against each other. It's going to be stripping off electrons and all kinds of things. So that's basically the idea you have to have in your head when you're doing this. And then it talks about cold welding, which is sort of irrelevant for this. I don't think that adds anything. You have the normal force against it. You have saying something that's like a jerky motion, like if you were pushing something, they're saying in a small microscopic sense, it's not even, so it's going to be like a starting and stopping and jerking. But the ridges are so small, you're not going to actually notice that. It's an imperceptible jerkiness. If you were to push something like a cabinet over a gravel driveway or something, right, you're going to notice that. It's going to, because of the way the rocks are rolling underneath it, and they're getting stuck, and then they're moving, becoming loose, that kind of thing. Okay, so now we're getting into the actual equation here. So the equation, as we write it a lot, especially you'll see it in lab more like this. You're going to have the force of friction, and then you're going to have mu. This is mu, which is the same as over here. And then this has a sub s. The sub s just means static. When we switch to kinetic, it's just going to be sub k, right? And then normally this is written as normal force, like so. It's just like a capital N. They want you to remember that it's a force here, so they've written it as a force, and then they have a sub N for normal, so it's just normal force. But you're going to see it most of the time written like this, just a capital N. So all this is the coefficient of friction times the normal force. So the coefficient of friction, you might ask, where does this come from? The coefficient of friction actually can't be determined in any way, shape, or form from purely like formulas. And when I say that, I mean like if you were just sitting in a room somewhere and you said, okay, I want to know what the coefficient of friction is of diamond sliding on tungsten carbide or something weird. And then you say to yourself, well, I don't have these things. I don't have a diamond or a tungsten carbide. Can I figure out what this is without having these objects in the room? And the answer basically is no, you can't. There's no good way of doing it. So someone basically has to test this, and they have to say, okay, what happens when I do this? They record the results, and then they just release the results for the rest of the world. So there was in the engineering building, I've seen the book. There is a book that is just purely coefficient of frictions. The book is literally like I don't know, about this tall. It's this massive book, and then you open it, and then like the binding of the book has to roll back and forth. This thing's so tall. And all it was basically a guy sat there and just tested things. He said, okay, I'm going to take this wooden block on metal. Okay, that's figured out the coefficient of friction from the experiment. Now I'm going to take a wooden block on rubber. Put it on there. Okay, now I'm going to take a wooden block on asphalt. Put it on there. Tested it thousands and thousands of times because there's so many materials, right? And everybody has a use at some time or another for specific materials against them, especially in engineering. So anytime you need this coefficient of friction, you just have to look it up. So that is the equation. You should get used to that. Again, we're going to use it for both static and kinetic. Again, this force is what you have to overcome. So if we apply a force, we're going to say, I'll call it force sub P, official P. We're going to say this is a pulling force. So for instance, this is going to be the same as taking something like a string to a block, for instance in lab, and then pulling the block up. So now you have a force that's pulling up. You are the force pulling it up. That's measurable. That force has to be greater than this force of friction here to make it move, right? When you do this in lab, and I don't know that it'll be explained to you, I'll probably post this for my lab sections also. I don't know if they'll make it this far in the video to see this, but there is a spring in lab, and the spring is a force meter. It measures force. And the way it works is it is just calibrated to show you the newtons, the amount of newtons it is using to do something. So basically the spring's in it. You attach it to the box. When you go to pull it, the one end of this thing is sitting still. You're pulling a spring like this, and then all of a sudden it jerks into motion and it, does this kind of thing. That can tell you exactly how the kinetic friction relates to the static friction, right? So you go to pull this thing, the string expands more and more, and then all of a sudden it jerks closed because you've overcome the static portion, and then it's going to stay closer together. So maybe it was like, turn a little bit here. Maybe you pull it, and it's like this far apart, and then it'll spring like this, and then as you pull it, it's like this. So basically the spring is compressed less during the kinetic portion, and it's going to be expanded more during the static portion. But you can measure the newtons of it either way. Another pro tip with the Newton meter, it's reading the amount of newtons no matter which direction you're applying it. So if you turn it sideways and use it as a spring, it's still reading the amount of newtons, but you have to take into account the gravity acting against it, right? So it's always a free body diagram. It's always giving you the information you need. It's up to you as the user to know that certain other forces are being applied. Or if you're using it at an angle, then gravity is going to work at it according to the components that you have to break it up into, right? So you need to break up to those components in X and Y and decide what's going on. Okay, I might have already explained most of this. We have the coefficient of friction. The values of the coefficients are unitless, and they have to be determined experimentally. That's what I just explained. Forces that applied at an angle. Again, as I explained, you're going to have to figure out the components always. So if you push something downward, then again, you have to break it up into components. If you, instead of pushing directly against something, you push up against something, right? That's going to have the components. So again, it's the same deal. We want to use free body diagrams. We want to break these things up into components and then be able to add and subtract them to see what's going on. A drag force. So drag force we get into a little bit in here. You'll get into this a little bit more if you're taking 182 in the future. You get into this a lot in liquids. So, but we also use it for airflow in this. I think maybe it's easier to picture in a liquid. So, for instance, if you took we'll say like a capsule or something like a pill, and you put it into a pipe, and the capsule's just sitting inside, and then basically water is going through the pipe, then the water has to streamline itself around whatever the object is that you put in the water, right? So this is moving through. Um, the water has to curve around. It creates like a little slipstream around it. We also put cars in like wind tunnels to figure out the aerodynamics to see how the air flows around it. If you made your car into just a giant block, like it literally looked like a brick, the airflow is just smacking against it. You're not making it easier for the air to go around it. So you're increasing the drag force. And by making a block, you have like maximized sort of the surface area of the front of the car. So you've made the maximum amount of surface push against the air, which is something you don't want, right? Okay, so they're talking about the drag force. That's the drag force moving against it. It's essentially the same as friction, only instead of just being applied at the surface, it's going to be applied around the entire object. So if I drop this through the air, same deal. Just think of the air as liquid. It's moving up around the object, and it's affecting it everywhere instead of just in a single plane. So again, same deal. It always opposes the motion that the object is moving in. So it's the same thing when you think about the planar friction. Yeah, so we'll get more into this. There's turbulent airflow, and then there's what they call laminar airflow. Turbulent is going to be, airflow that comes off like this. If you have some kind of object moving forward, we'll say it's moving this direction, you have this turbulent airflow. It's kind of unpredictable. If you watch like you have, we'll say, we have some kind of, this is supposed to be a little flame. I don't know if that looks like a flame. Who knows? It's a flame now, just believe me. So if you have like a flame and like smoke's coming off it or whatever, you'll see it'll tend to come up like kind of like this and move up, and it kind of billows out. This isn't really making sense when I'm drawing it. If you look up like smoke coming off something, you can see it. It kind of comes up and moves out. It's because the convection of the heat moving it upwards and then the airflow. And so it's kind of like an unpredictable nature where it's going. That's what it means by turbulent. Laminar airflow is basically like air coming in like this and going around. Right, so basically it makes these nice straight lines. It's predictable where it's going. You can see exactly how the airflow is. It's very predictable, and they all the streams of air that you can measure are going in the same direction. That has pretty much nothing to do with anything. Now you just know. Okay, so drag force, terminal speed. So again, getting away from the liquid analogy and then moving to objects falling, we're gonna get into terminal speeds, right? So a terminal speed, if you've never heard of terminal speed, there's a terminal velocity at which something, if you drop it in air, will hit because of air, because of the atmosphere. So if you are in a vacuum and you were to drop something, it will accelerate forever. There's nothing to slow it down. Gravity is always acting on it. So the further you get away from Earth and drop it, by the time it reaches the surface, the faster it'll be going. 1,000 meters per second. Pull it a little away, 100,000 meters per second. Pull it farther away, 1,000,000 meters per second. It's just going to keep going and going. But in the real world, we have the atmosphere. So the atmosphere is creating that drag. It's creating a friction around the object, and it's going to eventually equal the force of gravity so that you are no longer accelerating. You are moving at a constant velocity. Hopefully that makes sense. So you can see here, And physicists really like cats for some reason. So they have an example of a cat, but it's kind of terrible. They're dropping a cat. Um, so there's the force of gravity acting on this. So as you drop an object, the drag force is going to act against it. When you reach terminal velocity, the drag force now equals the force of gravity, right? That's when you know you've reached terminal velocity. So it's the same thing when a person jumps out of an airplane. There is a point at which you're not going to accelerate any faster. When you skydive, you jump out, you're going to accelerate, 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 and then your drag force is just going to be equal to the force of gravity, and then you're not going to accelerate anymore. So I'll wait for a future slide to explain like when you change positions and that kind of thing. But getting into this a little more, we have this drag force here, and then we have a formula for it. So you can see here that we have C. My little pen thing wants to work. We have C, which is listed down here. It's the experimentally determined drag coefficient. So this is basically our mu from previous, the planar problem, right? This is the same as mu. This is experimentally determined. It is a coefficient. It is a constant, right? It doesn't change. It's a single number. This is not a variable. It's a variable in the sense that if you change the conditions of the experiment, it's going to change, but for that experiment, it's a constant. This is rho, not to be confused with P. Rho is the air density. So for instance, if we drop something in water, then you're going to have to change the density to that of water and not air. But for everything pretty much we're going to do in here, it's going to be mostly air. This is just the cross-sectional area. So if I were, for instance, to take that same example I was kind of using before, where we have a pipe and something traveling through it. We'll say we have a smaller solid pipe moving through it. I don't know why that made a straight line right there. We have a solid, we'll say like a cylinder moving through it. This is solid, right? When you want to look at the drag force, you want to look not at the whole 3D object. You're basically breaking it down into a 2D object. Okay, sorry about that. Apparently the memory card was full, so I had to make room. Okay, so where were we? Again, talking about the cylinder and a pipe. The cylinder in here, the only thing you need for the drag equation is the area, the cross-sectional area. So that's basically if we take a cylinder of some sort and you're just taking a slice. So it's a two-dimensional slice. So you take when you go to calculate the volume of a cylinder, you have to first take pi r squared, right? Because you need the area of the circle. That is a slice, essentially. It has no height. It has no third dimension. So that's what we're doing, because we only need to know what's passing in pipes, usually at a certain point. We don't need the depth of it. When you get into the depth, then it's the amount of time something's passing through. But in this case, just doing something passing around it instead, you only need the cross-sectional area. So that's what this is. This is the cross-sectional area. And physicists break everything down into basic shapes, spheres, cylinders, occasionally cubes or squares for 2 dimensions. So usually it's very simple, whatever the shape is. We're not going to do something like a blob of goo and try to figure out the shape of it or something like that. Okay, so we explained everything here, and then you have the velocity which is moving, and it's squared. Okay, so again, you have the drag force, and this is only for something falling, but you have the drag force, the force of gravity working downward, and then the drag force working against it. And when you do the summation of these forces, you're going to get the whatever the resultant force is, right? You have some mass times some acceleration. A lot of these equations, if you did the problems in the last chapter, you're supposed to, you'll see you have to solve for a lot of accelerations because of blocks sliding on things, right? And as we explained, once these two equal each other, you're going to get a terminal speed. And then they just have an equation here simplified for a terminal velocity, basically. So you have the force of gravity on top, and then you have basically the pieces of what we just did, the C rho A, which is right here. And if you notice, all these things, C is a constant, rho is a density of whatever the fluid it's moving through of, and we count air as a fluid. You have the density of that's a constant. It's not going to change. And then you have the cross-sectional area of whatever it is. It's also not going to change. So this whole thing right here is just a constant. So when we look at here, this is divided by a constant. And then you have the force of gravity. So this is all dependent on the object and whatever it's moving through. So, and then they have a couple obvious things here. If you look at the math of this, if you reduce the A, then you increase the terminal velocity of something, and vice versa. So, and then it's talking about skydivers uses controlled descent. So, obviously, if you're falling and you spread yourself way out, you're going to make a bigger area, right? This will slow you down. So if you want to increase in speed, they can pull their hands in, make themselves smaller, and then they can tip themselves forward so that they're coming straight down. Want to slow down, you flatten yourself out. Much bigger surface area. This actually changes the speed quite a bit. It's very effective. Obviously, skydivers do it all the time. Okay, so here is a picture of the book I had to take. And I'll kind of just verbally run through the parts. Maybe you're not familiar with this. It is a simple problem. It's an example problem in the book. All of it is written there for you. You can see exactly what's going on, hopefully. But basically, it's a raindrop. You're figuring out the terminal velocity of a falling raindrop. And they give you all the information here. So it says a raindrop with this radius, this height, and as I taught you before, hopefully in the beginning videos, you kind of ignore the extra information here. So you have a radius, just not even reading this, you have a radius here. You have a height here. You have a drag coefficient, which is right here. And then this is kind of an important piece that's not in numerical terms, but assume the drop is spherical throughout the fall. And then you have the density of water here. So again, rho is commonly density for this. Sub W means water. So it's the density of water. And then we have rho sub A, which they're doing the density of air. And that value is here. So basically you have these pieces of information. Again, I would make a table somewhere like so. Say here's the variables. This is H. This is R. No longer looks like an H, but whatever. Hopefully you're listening. C, etc., and then write in the values. Then you know exactly how much information you have, how much information you need. And then, so they're talking about this. Drop reaches terminal speed where the gravitational force on it is balanced by the drag force on it. So the acceleration is 0, right? It just moves at a constant velocity now. The velocity is no longer increasing. And then we're going to apply Newton's second law. So if we go through this, again, we were supposed to assume that the water drop is spherical, right? So this is an equation you should definitely have memorized as an engineer or physicist, is the volume of a sphere. So 4/3 pi r cubed. This pops up all the time. Again, you should know this. Again, this is online class at this point, so you can look up all this stuff, but trust me, you're going to need this. Eventually, we're going to get past this online stuff, and you're going to have to go back to taking classes like regular and memorize things. So memorize this. You should always know it. You should know probably the circumference of a sphere, circumference of a circle, area of a circle, surface area of a sphere, all these things. And then we have density, mass per volume, standard formula. So we're given this formula down here. We have the force of gravity is the volume times the density of water times gravity. So we just plug in these values, right? We have the density of water. That was up here. If I can find my own mouse cursor. That was up here. And then we know the volume of a sphere, hopefully. And I can't. Where's the mouse? Okay. That's how bad it is. I can't even see the mouse pointer half the time. I'm sure you guys are struggling with it. But so you have the volume, density of water, gravity. So we know these three things. So we have Fg, right? So in the previous formula, right, we just looked at that. We have the formula for terminal velocity. So again, you have a bunch of constants and the force of gravity. Well, we just figured out what the force of gravity was down below. So you plug these in. So it's 2 times that 4/3 pi r cubed. And this is what you end up with. And then again, we have the density of water. And always be careful with the units. This is in kilograms per meters cubed. So that's good, standard units. And then you have gravity. And then we have a bunch of constants in the bottom. So basically, you just plug and chug at this point. You plug in the numbers, you get a value. They do this because it's kind of interesting. It says, what would be the drop speed just before impact if there were no drag force? So if you look at this, so basically if you drop of water, again, goes in a vacuum. Like we just remove the atmosphere. Say you go to the moon and you just drop a water drop towards the moon at 60 miles above the surface of the planet or something like that. Obviously, the force of gravity is different because it's the moon's gravity, not the Earth's. But you're going to have nothing to slow it down. There's no atmosphere on the moon. So it's kind of like the situation they're talking about. So we have this simple formula. Again, we were given the height. So you have all the information. You can calculate it. And then, of course, they're basically just saying that this is very fast, right? This is the speed of like the rifle from a gun. So I think the speed of like a 308 bullet, which is a fairly large rifle bullet, is going to come out about 300 miles per hour. This is going to be very similar to that. It's going to be very close to the same speed. So it would be moving very quickly, right? Okay, moving on from drag and friction and all this stuff. We are moving on to uniform circular motion. So one of the common things here, this is like some toy from the 50s. This was actually like a thing where people used to fling an airplane around, little propeller would spin. I only know that because I'm 100 years old. But very similar, you could think of if you took a ball on the end of the string and you swung it above your head like so. Most of the situations here are going to be very similar to that. So again, we already learned this in the previous chapter. Again, the velocity is constantly changing, but only in direction. You have a constant speed moving throughout, but the direction of the velocity is constantly changing. Therefore, it is an acceleration. So again, getting used to that concept, we move on. So the velocity, anytime you see capital T, like so, this is period. It's just always going to be period. This is kind of just the universal variable they use for period. Small t is time. Large T is the amount of time it takes to complete one revolution, which is period. So from the time it takes to go from here all the way around and all the way back, that's one period. So all the way around the circle and back where you started, that's one period. That's one capital T, which is listed right here, whatever. So then you have 2 pi r, which, if you remember, is the circumference of the circle. That is the linear distance that we travel around the circle, right? So if we put these things over top of each other, you have 2 pi r over the period. This is in meters. I don't know why this thing's struggling today. And then this is going to be in seconds, right? So you have meters per second. This checks out. It's a velocity. So yeah, nothing. Okay, so I am having technical difficulties. Internet's going in and out, screwing with stuff that I'm using here. I have this stupid school version of Office, so it's connecting to online and it's messing with things. Okay, so sadly I already went through a bunch of these slides and it didn't record because it went away. Hopefully it doesn't do that again. So I'm going to try to pick up wherever it cut out, which was around here somewhere. What I was saying earlier, and let me switch this back. Pen. What I was saying earlier was this is theta. And if we do our triangles, you do your geometry like usual, you can figure out what the angle of the velocity that's moving away from the circle. So if you want the tangential velocity out here, we can see that theta, if we make this into a right triangle, signify that as a right triangle. If you know what theta is, then you can figure out what alpha is, right? Because the summation of the inside of the angles of a triangle is 180. You can figure out, this one's 90, so you just need these two. And you go around there, and then you figure out that this angle here, beta, and this is alpha, you can make another right triangle. And basically, we just end up saying that beta equals theta. Beta equals theta. So you can, the angle of this by the angle inside is essentially what's going on here. Okay, so you have the change in velocity divided by the velocity, and they're basically breaking down these formulas to try to figure out where the acceleration comes from. If we look at this by units, which again you should be doing, which you learned in the first couple lectures, we have meters per second, change in velocity, so it's going to be 1, velocity 1 minus velocity 2, that sort of thing. And it's going to be divided by meters per second. Right, so this is going to cancel with this. We look at the other side, we have meters per second. That's multiplied by a time. So, I don't know where I wrote time. So this should be a second. So these cancel. So you're just left with a distance on top. Below, it's just a radius, which is a distance. So these cancel. So all of the units cancel in this. So this equation is correct. We know that we can continue with it. Now, if we look at this guy, we're going to have meters per second in seconds. So if we go to multiply these together, it's just going to be meters per second squared, right? Which we know is an acceleration. So we know that this guy here is an acceleration. And when you have velocity divided by time, that's an acceleration. So then you have, again, all they did was switch, like cross multiply here, your change in t with your v. So the v comes up here. Change in t comes up here, or came from here. And then so now we have v squared, and now we're dividing by change in t. So we got this acceleration here. So this equals v squared over r. This is your centripetal acceleration equation that we're going to use for uniform circular motion. Now we have our equation. Again, this equation is key for this section. And must be some shortcut to draw straight lines I don't know about. So this is the acceleration. The terms that are used here are centripetal, as we can see right there. And again, it made that straight line. So you got centripetal, and you're probably more familiar with the term centrifugal, right? So centrifugal is the acceleration that is moving outward from the circle. And this is the term that's commonly used in the everyday vernacular of the English language. Centripetal is actually the acceleration that we use that's pulling towards the inside of the circle. So they move in two separate directions. The centripetal acceleration is what we measure. The centrifugal is actually a fictional force. And we use it to counterbalance forces in certain situations, but we're not going to use it for right now. So which way will the object go? So basically, Object in uniform circular motion at point O, which is right here, is released from a circular path. So again, we're in the same situation where we're swinging something above our head, and then you just suddenly let go. You're saying, where does it go? Does the object move along the straight line path between O and A, or along the circular arc between O and P? If you've ever twirled something over your head and through it, you know it's going to move in a straight line, right? You've lost that center point that it's accelerating around, therefore it must move in a straight line. Okay, so again, we have our centripetal acceleration equation right here. And then they're using an example. They're using a car rounding a curve. Car accelerates towards the center of the curve due to the centripetal force, because that moves inward. Provided by the inward friction on the tires, your inertia makes you want to go straight ahead, so you may feel friction from your seat. This is basically the point where you're going around a turn and you're forced outward. These inward forces keep you in a uniform circular motion in the car. For a space shuttle, the shuttle is kept in orbit by the gravitational pull of Earth, acting as a centripetal force. So most people think that, like, when we launch something into space, like the space shuttle, the International Space Station, these kind of things, that it just because it's in space, gravity is minimal enough that it's just out there floating. This is not the case. It's not far enough away from Earth. It is still constantly falling towards Earth. So the space stations have a circular path, but then occasionally they have to push themselves further away from the Earth because they're constantly falling inward. They're spiraling inward, and they're eventually going to just crash into the ground. There was the Russian space station. I don't remember the name of it, but it was in the 70s, I believe, and they had just abandoned it. And so instead of trying to do something about it, all they did was just stop pushing it out and just let it continue along its natural path. And so it eventually just fell to Earth and burned up in the atmosphere. So like the space shuttle and stuff, it's moving at a significant amount of speed. It's like 26,000 miles per hour. And at moving at that speed, it can constantly outrun gravity, pulling it downward, right? So if you slowed it down to a stop, well, then it's just going to fall straight down to Earth. As you get farther and farther away from Earth, then it's not as effective as much. And then you get far enough space between planets and stuff, you're going to stop falling. That's when you're going to get that kind of free floating sensation. So that's what they're talking about here. Find my cursor again. So centripetal force, then we're just using the centripetal acceleration, right? Because this was just F equals ma. So the centripetal acceleration right here, we've just plugged in that we know. For the puck on a string, the string tension supplies the centripetal force necessary to maintain circular motion. So this is the force, right? So we have the mass of the puck. We're saying the tension of the string on the inside here is what we're equating to the force. And this thing's still moving in a circular motion. Checkpoint, maybe useful, maybe not. Every amusement park fan knows a Ferris wheel ride is consisting. So Ferris wheel goes around. The seats just kind of stay in place as it moves in a circle, right? There's 2 rotations there. The seat's constantly rotating. And then the circle's constantly rotating. So they're basically saying when you ride the Ferris wheel at a constant speed, what are the directions of your acceleration and the normal force from the seat? So remember, the normal force is always perpendicular from the plane that we're laying on. So that's the seat. So basically the normal force is always pointed up, right? Because the seat is always like this. Therefore, the normal force is always pointed up as we move in a circle. So that's what they're saying. And then they're saying when you ride a Ferris wheel, as you pass through the highest points, the acceleration is then downwards, and then saying here the normal force is upwards, right? So then at the part B, it's saying at the lowest point in the Ferris wheel. So now it's saying acceleration's upwards because of the circle, right? Maybe if I drew a circle, it would help. So when you're at the highest point here, we're pointing down, and you have FG pointing down, right? So this stays consistent. FG constantly points down. The centripetal force is pointing down when you're at the top. But when you're at the bottom, it's then pointing up, right? Because it always points towards the center of the circle. That's what they're saying. The magnitudes must be equal for the motion to be uniform. So we're not flying in or out, so they have to be equal. And then how do the magnitudes of the normal force compare to those 2 points? Fn is greater in B than in A. So that's the elevator motion that we experienced in the other chapter. So like as you accelerate upwards or downwards, your weight is going to change, right? So if we have the scale in the elevator and you start to move up, you're suddenly going to be heavier because it's going to push you down into the scale. As you come to a stop wherever you're going, it's going to deaccelerate, and so you're going to momentarily be lighter, so the scale is going to read less. That's what they're going for there. Okay, so bicycle going around a vertical loop, and I think there's a picture, basically just circle like so, and you got the little guy on the bicycle here. It's my excellent bicycle, and guy riding the bicycle. So he's basically going to go up this thing. He's going to go up, he's going around, and then we're going to have the bicycle here inverted. Whatever. Little dude. Apparently I can't draw upside down. He's going to be up here on the top of it, and then we're going to do a summation of forces. Right? So the normal force acting against that surface, you have the top of the arch. The normal surface, or normal of the surface, has to be perpendicular to the surface. So it has to be pointing down because the bike is pushing up against it. So normal force is pointing down, and I'll write that as normal. But then you also have the centripetal force pointing towards the center of the circle. That's the acceleration they're talking about here. And then you have also the force of gravity pointing down. So all 3 of these things have to be added together. So in this case, because they're pointed down, they've decided to make them negative. So all these things are going to be negative. So then you can plug in numbers and figure it out. But this is essentially what you're doing every time, right? If we did it from the bottom of the circle, then the normal force has to point up. The centripetal force has to point up. And then the force of gravity still has to point down. So now you're switching signs, right? So now these 2 are positive, this one's negative, so you're not purely adding all of them up. And then, yeah, we have the formula down here again you can plug it into. So uniform circular motion in a banked circle. So that means they call this like a camber on roads. So on roads naturally will tilt this way and this way. So they do this on sharp curves. They'll tilt it up because then it's harder for you to just go flying off the road, right? They do this on a lot of racetracks. Do it in like NASCAR. It's tilted up around the curves, and then when it comes back flat, it's flat like this. So you start to turn inward like this. It starts to tilt up, and then turns in around the curve. So yeah. So basically, when you're going around the curve, the car is like this. And we draw this free body diagram here. That's what's actually happening. This free body diagram is an angle like so. And then you have this car here. And I haven't made it very clear, but this is the back end of the car, right? This is like windshield. Okay, it's terrible. But this is the back end of the car, right? Moving around. So the normal force is over here. It's acting perpendicular to the plane of the slope. And then they're breaking it into components. So we have the y direction of the normal force. And then they're not using x here. They're just using the radial direction. That's what small r is. So they're saying the normal force in the radial direction is this Fn sub r. acceleration's moving inward towards the center of the circle, and the force of gravity is still acting straight down. So even though same deal as the box, it's acting, yikes, oh my god, I can't do it. Gravity is acting straight down, normal force is acting out like this, right? And then we're just taking the components, right? We're taking our sine and a cosine. So again, hopefully you got really familiar with this the last section with the inverted, or not inverted, inclined plane with the box on it. Again, you're going to do the lab on it. And if you do the math in the lab, same as the homework problems, you're going to get these tangents for the angles. And that's pretty much it. So you have the summary, and that's the end. So I will, this is probably longer, I don't know, because I had to cut it off so many times. So obviously there's 2 class periods to absorb this information. You can split the lecture up in 2 pieces. There's 0 point in telling you this now because you're at the end. I will try to do some problems later on and post them so you have an idea what's going on.